Alright, guys, so we've been looking at how mechanical energy hasn't been conserved, right? We've been looking at the fact that when you've got a non conservative force, a force that does not conserve mechanical energy, we'll see that our mechanical energy can go from 255 joules to 62.5 joules, right? Your mechanical energy can decrease. Sometimes your mechanical energy can even increase, right? If you've got a force doing positive work in the direction that your object is moving in, you can see your mechanical energy go from 50 joules to 75 joules. But basically, those forces do not conserve mechanical energy, they change it. Okay, now what about when mechanical energy is conserved? So that now relates to the principle of conservation of mechanical energy. This principle states that in an isolated system, mechanical energy will remain constant. Now, what does isolated system mean? An isolated system is basically a system where there are no non-conservative forces. So let me rephrase this. This principle of conservation of mechanical energy is saying when there are no non-conservative forces, so when there's no friction, no air friction, no tension force, no applied force, mechanical energy will be conserved. That's pretty much what it's saying. That part of isolated system is just referring back to the fact that we know all these forces that will change mechanical energy. They will decrease it, they will increase it, but in a system that is isolated, in a system that doesn't have any of those forces, mechanical energy will remain constant. Okay, now that's where this formula comes in. This formula basically says the initial mechanical energy is equal to the final mechanical energy. The only time you guys are allowed to use this formula is if there are no non-conservative forces in the system. Example here, we've got a 5 kilogram block starting at a velocity of 0, going down, and we can see that it is at a height of 5 meters above the ground. But the emphasis here, or the important thing to note, is that they say it is a smooth surface and there's no air friction. So we've now excluded the non-conservative forces. You see those forces that change our mechanical energy? They're not there. If it's a smooth surface, it means there's no friction. If there's no air friction, there's no friction, right? And then also, we need to think of, is there a tension force? Is there applied force? There's none of those here. So we know that here, mechanical energy can be conserved. So you can even calculate your initial mechanical energy because you know it's kinetic energy plus potential energy. So that would be a half times mass times the velocity, initial velocity squared, plus mass times gravity times the initial height. Then you can already see that this would be a half times 5 times 0 squared, plus 5 times 9.8 times the initial height above the ground, 5 meters. Okay. Right, we can already see and get the idea that this would give us 245 joules. We know that that would have been 0. Now, what about the final mechanical energy? You can also calculate the final mechanical energy and say kinetic energy plus potential energy is equal to a half times mass times the final velocity squared plus mass times gravity times the final height. So we can say a half times 5 times, but we don't know the final velocity. That is what we're trying to find. Plus 5 times 9.8 times the final height, which is 0. So what you end up having is a half times 5 times final velocity squared. This is your mechanical energy final. But now, look at this. Because they said there's no friction, basically there's no air friction, it's a smooth surface, so that means there's no friction on the surface either, there's no tension force, there's no applied force, we can actually say the initial mechanical energy is equal to the final mechanical energy. So that 245 joules that would be the same energy that you have at the final point. The final point here would have this energy of 245 joules because there are no non-conservative forces. This is an isolated system. So this 245 joules can come over there. And that would help you calculate what your final velocity is going to be. All right. So the main purpose of this is because I wanted to show you guys that this formula, this specific formula, can only ever be used if you're looking at a section like this one, where there's no friction, no applied force, no tension force, none of those non-conservative forces. I mean, obviously, when we look at this, we know that we have gravitational force though, right? Gravitational force acts downwards, but gravitational force is not a non-conservative force, okay? It is a conservative force. So whenever you don't have friction, tension force, applied force, air friction, know that you can very well use this formula. Let it be your saving grace, your first formula that you use.